Hey everybody. All right, so today we're going to be talking about piecewise functions. In order to do this, a couple of things. First off, strongly encourage that you have the notes in front of you because we are going to be doing some graphing. In addition, I would also like to say I'd recommend a couple of colors in front of you, at the very least a pencil. I wouldn't recommend a pen, but anyway, that's your choice. You do you. Before we get started, what do I have to talk about? I need to talk about the alligator in the room. Okay, not really. I need to talk about the inequality symbols. And if it's been a little while, maybe this looks unfamiliar to you, but way back in the day when I was, middle school, elementary school, whatever, my teacher was all like, whatever side the alligator's eating, that's the bigger side. Okay. That's not super helpful if you don't understand what the heck is going on. What this really means is when you see a symbol that looks like this, like a triangle where the bigger side is on the left, that reads as greater than. All right? When you see the alligator pointing to the right, the mouth of it opening to the right, that means you're reading a less than symbol, because what you're focusing on, people, is the fact that this end is wider, this point is less, it's smaller. And then if you toss a line underneath it, you get equal to, greater than, or equal to. All right, equal to. Let me point out what this translates to in graphing world. If you see a greater than symbol, open dot. If you see a less than symbol, open dot. Okay? If you see a greater than or equal to, you close that dot right up. If you see a less than or equal to, you close the dot right up. That's why whenever we graph equations, everything's a dot, because it's equals. All right? All the dots, all the points. Okay. So that's my little reminder on those symbols, which we are going to need because we are going to be graphing pieces of functions, okay? So that's what a piecewise function is. It is pieces of separate functions put together. Why is it called a function? Because at no point in time does the function have two different values. That means two different outputs for one input, okay? And here we go. So depending on who you are, you may want to highlight this stuff. You might want to color code. That's your life choice. What we're going to do first is we are going to graph g of x, a function that is a line because it has a slope of 1/2 and a intercept at 1. We're going to graph that less than 4, okay? So I'm going to draw a little dotted line at x equals 4. Why am I doing that? It doesn't really need to be in the graph. It's more to give you a reference point to where you're going to stop graphing this line, okay? Because this line has a y-intercept at 1 and a slope 1/2. But you see that at 4, that's where you stop because the graph only exists less than 4. You could keep going down 1 and back 2 if you want, but you can't go any farther to the right. Okay, so now I'm going to erase this. Okay, so this currently is the graph of g of x, 1/2 of x plus 1, where x is less than 4. That's all the x values less than x equals 4, okay? Our second graph that we are going to create is h of x, which is another line with a slope of -1 and a y-intercept at 6. And we're going to graph this. Oh, and I should point out, my apologies, that because this says less, this dot right here should be open, okay? Hence the pencil, right? No big deal if that was a pencil mark. If that was a pen mark, you'd be like, oops. Okay, so we need to graph -x plus 6, where x is greater than or equal to. So this means greater or equal, close dot, okay? So we have to figure out where that dot goes. Well, you're going to go to 6. 1, 2, 3, 4, 5, 6. But that's not part of the graph. You're going to go down 1, right, slope, down 1 over 1, until you get here at 4, and then you go, okay, that's where my graph actually starts. Because all these other little dots were before 4. I can only graph this after 4. All right, so as I was saying, now this line has a slope that's negative, so that graph's going down. Okay, so now we have just graphed a piecewise function. We have our two pieces. We have g of x over here. We have h of x over here in pink. Okay, what are we going to do with this? Well, we're going to talk about what happens at x equals 4, because that's kind of the key point here, okay? So, well, a couple of things are happening at x equals 4. Main thing that we need to discuss is the fact that the graph breaks. Now, what's the fancy word for this break? It's discontinuous. Continuous at x equals 4, okay? Continuous is when you could run a pencil along the graph and the entirety of the graph without picking it up. Here, at 4, I got to pick it up to get to this other piece, okay? So it discontinues. It's not continuous at 4. Okay, and that's significant to us when we begin to talk about limits, okay? So we're going to get to that in a sec. So if we were going to, so the key thing is that we're discontinuous. That means there's two different values going on, okay, at 4. But we're still a function. Still a function, okay? Because we only have one solid dot, okay? If I had left that as a solid dot up here, then this wouldn't be a function because we'd have two x values at 4, and that does not a function make. It breaks the vertical line test. Okay, so we are going to call this f of x, and I'm going to show you what the notation looks like when you put the two pieces together. So f of x equals, and we use these fancy brackets because it's like the combination of a half of x plus 1, where x is less than 4, right? So basically I'm just taking all this information, and then negative x plus 6, where x is greater than or equal to 4. I always like to write the functions from left to right, like top to bottom. Okay, so this function here was the first one we graphed, so that came first in my list, second in my list, and so on and so forth. Okay, so then if I wanted to perhaps evaluate, for those of you that maybe have forgotten what this vocab term means, literally just means find me the value. What is the y value at these given x values? So I'm going to go to the graph and I'm going to look and be like, where is 0? All right, 0 is right there on my x-axis. So 0, 1. So the answer to this question is 1. Okay, what about 4? Where is x equal to 4? Ooh, which one is it? Well, which one does it equal? It equals and is closed at 2. That's a height of 2. Okay, so 2. And then last but not least, what about 6? If I go to 6, 1, 4, 5, 6, it looks like it has, my graph has a height of 0. Okay, so we're looking for the y values at each of these places, okay? So if you're asked to evaluate a function, especially if you have the graph, just look at the function. If you didn't have the function, you would just plug these numbers in depending on the value. So since 0 is less than 4, that's how you'd know you'd plug it into the first function. 4, well, which is equal, 4 is greater than or equal to 4, so that would go into this second one. And 6 is definitely greater than 4, so you'd plug 6 in here. So that's another way you could figure out the answers to that part of the question. Okay, so moving along. How does this relate to limits? Okay, so first off, I'm going to give you a minute or two to just try and graph this function, okay? I'm going to have the graph pop up in a second, and then I'll talk to you about part B. So right now, you do part A. Ready, set, go. Folks, here we go. So in case you need a little review on just like these different pieces, just remember to look at the equation and kind of identify what should this shape be. So in purple, that first shape that I have is a line because this equation is to the first power, right? So we're looking at something that's linear. All right, second thing, number. So because it's just at one place, this ends up being a point. Sometimes this could turn into something that's like a constant, you know, like a horizontal line, okay, if it's for a longer period of time. And then this last thing with that squared is a quadratic, all right? And it's negative, so it's going to be some sort of parabola, depending on how much of it you get pointing down. So these are our three pieces kind of color-coded for you just to help you identify the different parts. So how does this relate to our whole limits conversation? Well, each of these pieces is, especially at 2, kind of the pivotal location right here, doing something a little bit different. So if I look at the limit as x approaches 2, and I look only on the left side, then I'm looking at this purple shape, and I'm looking at the purple shape. What is it doing as it's getting closer to 2? That's all I'm focusing on, that part to the left. And that part, that is definitely getting closer to a height of 1. Okay, so that's going to be 1. That's that limit. Okay, so that's the left-hand side. Then I ignore everything else except for the right-hand side for a second, and I go, okay, what is this function? So we're looking at this overall shape that's the part that's moving. From the right-hand side, it is somehow going up, coming back down, and curving, and getting closer to 1, 2, 3, 4, 5. Okay, so that limit is getting closer to 5. Okay, here's the sitch. These two things, these are not the same value. I think we can all agree 1 is not 5. Okay? So if 1 is not 5 and 5 isn't 1, then this limit does not exist, because the most fundamental and important part about limits is that the left-hand limit has to be equal to the right-hand limit in order for the limit to exist. So you must have the left hand equal to the right hand for the limit to exist. All right? If it isn't true, if that isn't true, then the limit is a DNE sort of situation. Okay? That is the key, really, of this lesson for today. Okay? And to kind of summarize that, we are going to write down a couple of things. All right? So, conditions for a limit not existing. Okay? By the way, I should go back and just say, like, this, basically, anytime you have 2 pieces approaching a value, an x value, and they don't meet, the limit at that location will not exist. It is entirely possible that a limit can exist separately on just the left side or just the right side. But as a whole, that limit cannot exist. Okay, and that's basically dealing with the fact that this is discontinuous. Okay, so let's kind of get this stuff on paper. All right, okay, so pivotal key things. First off, the first condition for a limit not existing is what I just demonstrated to you. It's when, so the first situation is when the one-sided limits are not equal. Okay? So basically, the limit of as x approaches c from the plus side of whatever your function is doesn't equal the limit as x approaches c from the negative side of whatever your function is that you're talking about. If those aren't equal, no good. Okay, option number 2. What is another situation in which you won't have a limit? Well, if the function doesn't approach a particular value. The function, it would typically be what